Okay, we're recording, yes. Here we go. We're on page 38. We're going to spend a little bit of time, a couple days. We're going to talk about velocity time graphs. So Taylor needs to include page 38 in her blog for the day. Oh. All right, page 38. Okay, analysis of VT graphs. In the last chapter, we found velocities from displacement time graphs. We spent a lot of time in grade 11 on displacement time graphs, so now we're going to spend more time on velocity time graphs by taking slopes at different times. In this chapter, we will use these values to create velocity time graphs and analyze them using the three primary analysis methods for graphs learned in the last chapter. So first of all, let's remind ourselves about constant velocity graphs. Now what I would suggest you do is I'm just going to make notes right on this handout. Basically what I did was I photocopied all of the graphs and important parts and put them on the page so you guys can just fill them right on that sheet. Okay? Right on that sheet that I gave you. Exactly. So, for example, a motorcyclist traveling along a straight, level road past markers at 40 meters, 100 meters, and 160 meters at the times you can read on the graph in figure 2.1a. That's the graph here on the left. This DT graph is a straight line. The slopes at 3 points in the graph are recorded in the table of figure 2.1b and plotted on the VT graph in 2.1c. The horizontal line on the VT graph shows that the velocity of the motorcyclist remained constant as time passed. Use the read, slope, and area techniques of graph analysis to discover what information can be gleaned from a VT graph. So once sort of in a bit of a nutshell here, the motorcycle is traveling at a constant speed. This is a position time graph. We can tell it's a constant speed because the line is straight. Okay, and you can see here that they actually found the slope at 3 different times. They found the slope there, it's 20, there at 20, there at 20. Obviously all the same because it's constant. Straight line. Then they recorded those values up here, and then they drew a graph. And you'll notice that the velocity time graph is in fact straight and flat. 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 Now, can you tell me from the DT graph how far did this motorcyclist go?
Time position, yes.
200 meters. How would I get that 200 meters? Right, you are, Jory. How would I get that 200 meters from the VT graph? From the VT graph.
You have to go V on the T. V equals D over T.
Remember?
10 seconds.
Exactly. So in fact, Zach's saying 20 meters per second times 10 seconds. What you're actually saying, Zach, is we would find the area. Remember that?
Yeah.
Finding the area?
Area.
Remember that? So to find the displacement from a VT graph, we find the area. Okay, so reading the graph. In figure 2.2, the units on the y-axis are meters per second, which indicates velocity. Since you're reading a given velocity at a given time, reading this graph allows you to find instantaneous velocities. Finding the slope of the graph. To find the slope of the graph in figure 2.2, okay, that's that new one, this one here, basically the same one. Note that the horizontal graph has no rise, thus the value for any delta t, the value of delta v will be 0. The value of the slope will be 0. So what does that tell me? The slope of this is the acceleration. The slope of the VT graph is the acceleration. Because it's flat, we would say that the acceleration is 0. It's not speeding up, it's not slowing down, it's moving at a constant speed. You should be able to get constant speed a variety of different ways. Slope of this is straight, constant. Here the slope of it is flat, 0. Acceleration is 0. The slope calculation produces a value of 0 with units in meters per second squared. This quantity is the change of velocity over a given time period. We can see that if the object has a constant velocity, its acceleration must be 0. The process of changing the velocity is called acceleration. We've talked about that already. The units for acceleration are distance over time squared, and you get blah, 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 blah. A equals delta v over delta t. Old hat to us. Calculate the slope from 2 points in the VT graph gives us the average acceleration. The slope of the tangent on the VT graph gives us the instantaneous acceleration. Now, we don't need a tangent here because it's already a line, right? It's already a straight line. Okay, finding the area under the graph. Everything above is positive, everything below is negative. Blah, blah, blah. We know all that. Okay. Now, do you guys have something at the bottom of this page? No. Yes, you do, right? You have...
Yeah.
Oh, yeah. This just shows positive displacement, right? This shows negative displacement. Now, what I did was I copied that part there. I left out sort of the what does it lead to at the bottom of page 39. So you should copy that in. So if you have a VT graph, what do you get to read from it? You get to read meters per second, which is in fact the instantaneous velocity. The slope of the VT graph is meters per second squared, which is going to give us the acceleration. It's also on the bottom of page 39 there, if you want to follow along there. The area we get a unit of, when you take meters per second times by seconds, the seconds cancel and you end up with just meters, which is the displacement. So the VT graph is quite valuable. It can give you all three things. Okay, so moving along, graphs with changing velocity. On a performance test, the Honda Civic produced the DT graph in figure 2.5a. As you saw in chapter 1, a curved DT graph means that the velocity is changing. Finding the slope of this graph at 4 different times gives the velocity as shown in figure 2.5b. Plotting these points gives the VT graph in 2.5c. So what they did was they took 3 positions. The first one you can barely see because it's right at the start. So there's one there, one there, one there, one there. They did tangent lines. And they calculated the slope of those tangent lines and recorded the values up here, 0, 6, 12, and 18, right? Slope here is 0, slope here is 6, slope there is 12, slope here is 18, which tells me that the velocity is increasing. The velocity is increasing, right? And so I get a straight line, but it's increasing, right? So if we find the slope of this graph, right? If I find the slope of this graph, I get, and you can see the figures there, they've got the slope is 12 over 3. We get 4 meters per second squared. 4 meters per second squared. Has an acceleration of 4 meters per second squared. Every second, the speed increases by 4. If we find the area under this graph, the area under the graph in figure 2.6 is a triangle. I'll go in blue here. It's half the base times the height. By substituting values and units in the graph into the equation, we obtain half the velocity times the time, and you get, now how did they get 4? Oh, 1/2 of 14. How did they get 14? Well, they only went to 3.5 seconds. Why did they do that? Oh, they're talking about, I'm missing a graph here, aren't I? Do you guys have that one at 2.6 at the bottom left-hand corner? Yeah. Yeah. Why would they do that? That's stupid, isn't it? Okay. Well, the textbook is talking about that graph at the bottom there. If we were to find the total, we would probably want to go to 5 seconds, would we not? Because that's the total one there, right? Let's do that. Right. I'm talking about this blue area of this one here. So we would have 1/2 the base times the height. We would have 1/2 of 5 times the height of 20, which is going to be 50 meters. Yeah, this one here is 50 meters. They did another one there. They only went to 3.5 seconds. I don't know why. And then they do something stupid and talk about 6 figs. Okay? Everybody good? It's all sort of kind of review, right? Right? Okay, moving along here. Example number 1 on page 41. Repeating the test drive in 2.5 in a westward direction produced the VT graph in figure 2.7. That's this one right here. Now, it's westward, so it's to the left, and so it's negative. Calculate the acceleration and reconstruct the DT graph. So finding the acceleration, you have to find the slope, right? It's a negative slope, and they end up with -8 over 2. -8 over 2, or a slope of -4. Right there, Annie, before you sit down. One of those sheets right there. They get a slope of -4, and that's going to be meters per second squared. And we're on page 41. Okay, so we get an acceleration of -4. Now, what about displacement? To find displacement, we once again find the area. This time the area is under the time axis, right? And stretches down to the velocity line. 3 areas are shown in figure 2.8. Figure 2.8b is the table of displacements represented by the areas under the velocity graph. These points are then plotted and joined with a smooth curve. So In the first case, they're on page 40. They gave us a displacement curve, but in the second one, when it went backwards, they didn't do the displacement curve. And now they're asking you to create it. How do we get displacement from a velocity time curve? Finding area, right? How do I get the graph? I don't want just one displacement. I want the displacement graph. So what they're saying is break it into parts. So there's like part A, and then there's part B, which includes A and B, right? And then C is, well, actually, they don't break it down like that. They break it into A, B, and C, and then they add them all together. But same idea, right? So they found the value of just A. It's minus 4.5. Then they found A and B together. They got minus 18. Then they found A and B and C all together, and they got minus 40.5. And then to get the displacement time graph, what do you have to do with those? Just do what? Just graph it, right? So they're taking these individual areas of a VT graph, finding individual areas. They got 0, minus 4.5, minus 18, minus 40.5. And then what did they do here? They simply graphed it. Here's 0. 4.5 is right there. A plus B is minus 18, which is right there. And A plus B plus C is minus 40.5, which is right there. And once they got these points, then they connect them. Does that make sense? I got a few blank stares out there. I'm a little bit worried. They asked me to come up with the displacement time graph from a VT graph. Okay? Up to now, all I'd asked is what's the total displacement. This time they're asking for a graph, and so you have to do more than one displacement and then just connect the dots. Then you find the slopes, right? You would find, if you were going the other way, that's a good question, Quinn. We would find the slope there, the slope there, the slope there, and the slope there. And then you would get these points right here, wouldn't you? And then connect. Right? Good question. Good question. All right, that's good. Different, yeah, lots of pages. Page 42, the velocity and acceleration have different signs. So automatically, if the velocity and acceleration are going to have different signs, this thing's going to be speeding up or slowing down. If the velocity and the acceleration have different signs, it's going to be slowing down. Okay, we're on page 42. The signs. Like the velocity is positive, the acceleration is negative. The velocity is negative, the acceleration is positive. We're on the top of page 42.
That means it's going to be negative?
What's going to be negative? The velocity is positive, the acceleration is negative. Or the velocity is negative and the acceleration is positive. They have opposite signs. Okay? Different directions. If they're opposite, it's slowing down. Yeah? Well, okay, let me put it this way. Okay, let me just, right? If the velocity is this way, right, and the acceleration is that way, it's going to be slowing down. If the velocity is this way, right, and the acceleration is that way, it's going to be slowing down, right? Right? Doesn't matter. Slowing down. Yeah. Okay, so for the slowing down portion of the roller coaster ride, find the acceleration. For this case, we're going to use the DT graph in figure 2.110, this one here. Figure 2.10 shows the process of creating the VT graph from slopes on the DT graph. To find the acceleration, take the slope of the VT graph. Now, this is the position time graph, right? So, they found the slopes here. They found 3 values for slopes, Mary. They found the slope here, they found the slope there, and they found the slope there. Okay, they drew a tangent line. They got a slope of 30. That slope is 30 in red. The slope here is 12, and the slope here is 0. They found 3 individual slopes, and then they graphed them. 30, 12, and 0. the velocity goes down to 0, which means the object is doing what, Zach? Stopping, slowing down, right? The velocity starts at 30 and it goes to 0. It's slowing down. If I then take the slope of this, it's going to give me the acceleration. So that's going to be a negative slope, obviously. It goes down 30, so that's going to be minus 30 over the time of 5 seconds. My acceleration is minus 6, which is what it shows in the book. Okay. Figure 211 at the bottom. I didn't copy it, but we might want to take a quick look at it. Determining the action of the object. Okay, so it's a VT graph. I'm starting on the left-hand side there. Take the slope and find the acceleration. If the acceleration is 0, then you have a constant velocity. If the acceleration is not 0, then is the sign the same of the A as the D? The answer is yes, it speeds up. And if it's no, then it obviously slows down. So, example number 3, a lot of traveling and ending up nowhere, which sort of feels like physics class sometimes. You can see in the background there on the book, you can't really see it on your sheet, but can you see the green hill in the book, in the textbook? Yeah, it sort of looks like that. Yeah, yeah. In the book there, you can see the hill. Now, you got to be careful here because it's a little bit deceiving. Figure 212A is a VT graph of a cyclist's motion. The cyclist traveling at 20 meters per second arrives at the bottom of the hill, climbs up the hill to a stop, and then coasts back down again. Find the total displacement as well as the acceleration for each section. Now what they're talking about is the vertical displacement, because obviously if the guy's going up a hill and down a hill, he's going sideways, right? They're talking about the vertical displacement. In fact, you should probably say that in the book. In fact, if you don't have that on page 43, write in the textbook.
I'm not doing that.
I want you to write in the textbook.
Okay, right in the textbook. Awesome.
What does it say, Zach?
Find the total vertical displacement.
There you go. Where does it say it?
Oh, it does say it.
It says that vertical on some of these below there.
Excellent. If yours doesn't say that, write it in. Find the total vertical. Mine doesn't say it. I'm going to write mine in. No, don't do that.
69.
How to spell vertical?
First and then the second.
Find the total vertical displacement. They spelled vertical wrong?
That's what everyone finds like really good movie volume.
Yeah.
Oh, I just said that it was in my.
Okay. Okay, so how do we find the displacement, right? This is a VT graph. How are we finding the displacement? We're going to find the area. So what's the displacement of part A over here?
40.
A is going to be 1/2 the base, which is 4, times the height, which is 20, sorry. So that's going to be 40, plus 40 because it's above. This is B down here. So that's going to be 1/2 of also 4, but this time minus 20, which is minus 40, giving me a total displacement of 0. Total displacement of 0. 1/2 times 4 times 20. 1/2 times 4 times 20. You'll also see that at the bottom of page 43 of the book. 20. 20. Okay. You're going to have to get out of the idea of, follow along, because the prof's not going to hear you, and you're going to have to figure that out. So you're going to have to figure stuff out when they can't write, because they will be able to not write. And there's okay. So the money ball is blah 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 blah. The money ball is on the bottom of page 45. Right? This is information obtained from a VT graph. So let's fill this in. Isolation, boys, let's go. Okay? Very similar to the Rampton flowchart. Information from a VT graph. So, from a VT graph, what do we read? We read instantaneous velocity. Quinn, I need like 3 more minutes.
What happens now?
I guess you're tied. From the VT graph, slope gives us acceleration. This is again on the bottom of page 45. If I find the acceleration with 2 points, well then that means I'm finding average acceleration. Okay, 2 points on the bottom of page 45. I'm recreating that chart on the bottom of page 45. If the acceleration is found with 1 point, which means a tangent line, then that means I'm finding instantaneous acceleration. And if I find area, well then that gives me displacement. And if I take area divided by time, well that gives me average velocity. Really, this little chart thingy here is exactly like I showed you the other day. Those 2 column charts, you know, it's basically the same information, is it not? Pretty much. Just sort of, you know, mixed up, reworded a little bit differently. Okay, so I'm going to stop there. I'm going to give you some time to work. There's some questions on page 46, 1 to 4. There are some questions on page 69. Now, I believe those ones on page 69 are graphical ones, and so what I've done is I've run off those graphs for you. I just have to go and do that. But I have copies, so you don't have to mark up the textbook. Okay, so start with page 46, 1 to 4, and I'll go get those graphs for you.